So the goal today is to talk about linear operators. I at least certainly anticipate that I will finish the lecture part early, and then we can look at some problems, things you might have questions about. If you don't have questions, I forgot to bring my textbook, but I was going to look at, just some questions from the textbook, things that I can lead you through. You can always look at the website I showed you with all the solutions for the textbook problems to get, other views on it. So starting off, what an operator is. Okay, you guys are both in linear algebra, probably a little ahead of linear algebra on this topic. I talked about it some last class period already. So the operator, here I have the word, it's a mapping between two function spaces, or in linear algebra terms, a mapping between two vector spaces. So that mapping means that it's something that's going to take information out of one space into another space. So out of the wave function space into our whatever variable space we're looking for. They don't always return the same function, but for quantum mechanics, they do. So I have this question at the bottom. Is the wave function shown to the right? We did this last class period, sadly. I just jumped ahead. Is the wave function shown to the right a function of the momentum and kinetic energy operators? So we're going to check to see if we take the operator p hat and have it act on psi, if that gives us a value multiplied by psi. That's the check. And then we'll repeat it for the kinetic energy operator. So we just start off with the momentum operator is this, so p hat psi is equal to minus I h bar d dx simple enough, right? You do remember this from Friday, right? When we did this before? Yeah. I say right a lot, right? So doing the derivative, I'm going to have, of course, the minus I h hat stays the same, and the a is a constant, so it's unaffected by the derivative. Derivative of sine kx is k cosine of kx, which is not multiplied by this here. That doesn't exist in this. Now, I suppose one could say, oh, I can find a way. I could say minus I h bar k, well, let's just put a cotangent of kx times a one could put it like that. That is mathematically correct. But that there is not going to be our momentum because it's a function of x. We want to find just the momentum. And so psi is not it is not a function of the momentum operator. Now we go to kinetic energy. One tends to have a preconceived notion that if the momentum is not an operator of this psi, then momentum squared isn't going to be an operator of psi, right? It seems to make sense, but we're going to check. And so now I got a little gruesome in my putting the second derivative, right? I did second derivative is derivative of the derivative, which is actually how you get there when you have the momentum operator squared. So now if I do the second derivative of sine kx is, well, let's put out the constants first. And the second derivative of sine kx is k squared times minus sine of kx. And now we look at this and we say, aha, we are back to having psi. And so that means this here must be our kinetic energy. So in this case, we got back psi, which means that we're able to get our kinetic energy. The psi is an operator of the kinetic, or is a function of the kinetic energy operator. So even though momentum psi was not a function of that operator, it is of the kinetic energy. So I can simultaneously know the kinetic energy and the position, but I don't at the same time know what the momentum is. And it seems kind of odd because after all, kinetic energy is p squared over 2m. Can't I take that kinetic energy and calculate momentum? I can calculate a value, but it's not going to be an exactly known value. If I know exactly the kinetic energy, I don't know exactly the momentum. I have some uncertainty with it. Now, other things here in the terminology I'm trying to say is function of the operator. So this psi is a function of the kinetic energy operator, but not of the momentum operator. Right? You might have noticed me stumbling over those words a few times. I did a calculation of trying to calculate the expectation value for momentum yesterday, or Friday. And calculating the expectation value of momentum requires that I'm going to have the probability times the momentum value. But if it's not a function of the operator, I'm not going to end up with the psi mod squared, the probability part. And so I would have to go back and review Friday's notes to see exactly what I did with that. I don't know if I made a mistake or not. I have to go back and look. But you have to be a little bit careful in, finding the expectation value of an operator that is not an operator of the function. Now we have a few rules for our operators. The operators must be linear and they must be Hermitian. The Hermitian is not a topic we're going to talk about today, so we're just going to look at rules for operators. And this first rule is called the distributive property. I couldn't remember the name for the second one, and so I didn't put down either of the titles because I felt silly having one with the title and not the other. But the first rule is if I have an operator acting on two functions, that is, the operator L here is operating on function f plus function g, that has to be equal to the operator acting on function f plus the operator acting on function g, which is a property that multiplication has, right? So we tend to think of that as a universal thing, but it doesn't have to be. You can find operators that violate that. And then the second one, the operator acting on a constant times a function must give me the constant times the operator acting on the function. And yeah, I can't remember the name for that one. It's probably commutative property, isn't it? But it's only commutative with constants. So let's check to see which of the following are linear operators. So this one, the first one, the operator acting on function x, wow, let's get rid of that. There we go. The operator acting on function x gives us function x plus x squared. We have two tests. So I'll take this and put it through the two tests. The first test is, does operator 1 acting on f of x plus g of x equal operator 1 on f of x plus operator 1 on g of x. I don't have to know what f of x and g of x are to do the test. All I have to know is what the rule is and how the operator functions. So let me have Indy verbally lead me through this first check. What do I have on the left? Okay, the left side is really simple. What do I have on the left side when I do this calculation?
So you have the operator multiplied by the addition of fx and g of x.
That's very true of what I wrote. I should have been more specific. When I apply the operation, when I apply this rule, so my entire function is this. What do I get by applying that rule?
Just get the operator times fx, right? It's just
Well,
what it is.
I want to apply this evaluation. So I'm going to have this now applied. So I replaced f of x with f of x g of x. And so what would I have on the right-hand side if I have operator 1 on, instead of just f of x plus g of x?
Oh, well, you'll have operator 1 times fx plus operator 1 times g of x.
Still not what I'm looking for. I'll show you, because I mean that's why we do these problems, so you understand what the actual test is. So applying what I have in the green box, just let me zoom out a little. I will have first the function that was inside the parentheses. So that's replacing this here, plus x squared. Do you understand the method by which I got there?
Yeah, you just plugged it in as f of x, you have f of x plus g of x.
Right. I was trying to articulate that, and clearly I wasn't making it clear what I wanted you to do. Seeing it helps you to understand how to do the test. So now, and Christopher, what do I get for doing it on the other side? So I have operator 1 just on f of x, which you can read.
We said that f of x is fx plus g of x.
No, on the right-hand side, we now are doing just this one, and then we'll do that one separately. So in this first, in the green boxed equation, I'll replace f of x with f of x, which is why it's trivial. So what do I get for replacing f of x with f of x? I get, on the right-hand side, f of x plus x squared. Somehow I changed colors. So that's what I got from that one. But then I'm going to have plus what I get from doing it on g of x. So now, doing it on g of x, what do I get?
G of x plus x squared.
Right. So now the question is, are these equal to each other? No. So since they're not equal to each other, this is not a linear operator. So that's the test. In the homework that'll be due a week from today, you'll have some test this operator to see if it's linear. So that's the first test. Let's go ahead and run the second test just to make sure if it passes it and how we would do the second test. So to do the second test is, goodness, operator 1 on a f of x. Is that equal to a times operator 1 on f of x? So for this function, I would have operator 1 just replacing f of x with a f of x would be So that's the left side of doing the substitution. And the right side is going to be so are those equal to each other? Nope. Failed both tests. So now let me just split these up. So Chris, do you spell it with an I-E or a Y?
Y. Y.
Okay. So Chris, you go ahead and determine if operator 2 is linear or not. And Indy, determine if operator 3 is linear or not. And then I'll have each one of you explain your answer. And let me point out, once you find a failure, you don't have to do the second test, because if it fails, it fails.
Could you scroll to the right a little bit?
Here, that way we can see everything. Right then.
Ready?
I'm ready. You guys, I'm just waiting for you guys. You guys both done?
Yeah, we're ready.
Oh, sorry. Okay, so let's go ahead and just do Chris first.
So I said no because when I did the first test, I found that I got the value fx plus g of x squared, which when you FOIL that out is not equal to fx squared plus g of x squared.
Right. You've got the cross terms. Okay, so that's all you had to do. How about you, Andy?
I said yes for mine.
Okay, and what's your reasoning?
Because I did the first test and But I don't know. I guess I'm more confused on this one. I thought it was.
Okay, well, if it helps, you're correct.
Okay.
Because you have, for your first test, when you do that, you're just going to, the operator is replacing x with 3x squared plus 1. So that's going to be, everywhere the x appeared, I'm just changing it to 3x squared plus 1. Right, so x appeared 2 different places, so I had the substitution 2 places. And then if I do the other side of it, it's exactly the same thing. So that's the first test. Now, since it passed the first test, you also had to do the second test. And so the second test is going to be there's no x in the A, so the A is just constant. And there you have it. They're the same. And so it passed both tests.
Okay, so whenever you do one, you have to go on to the other one then? Like
Yeah, if it passes the first one, you have to do the second one because it has to obey both of those rules.
Right. Okay.
But if it fails one, you don't have to do the second one because it failed. Okay, back to this slide. I thought about it because I was, like, how did that lead to that? Right, this equation. And this equation in and of itself did not lead to the conclusion of if we know exactly the momentum, we have no idea what the position is. That's where I was trying to draw a wrong conclusion. That's just relating the wave numbers or the wavelengths with momentum so that we can look at these graphs and say the uncertainty in K, in the wave number, or the wavelength if you prefer, is a proxy for the uncertainty in momentum. And so when we take, by the way, I tried to go to this, I don't know if it's something with our firewall. I couldn't go to that web page this morning from my office. So I don't know if it's a dead link now or if it's our firewall. So I left the link there, which, it's unfortunate, but we're not really talking about the Heisenberg. I just wanted to make sure I got to this so I could explain what I was thinking on Friday. So this equation here was just to let us know that we can use the uncertainty in wave number as a proxy for the uncertainty momentum because it's just a constant h bar between them. And so then if we take a distribution in wave number space, convert it to a distribution in position space, we have the uncertainties in both of them. And if you have a wave packet that is a very, very narrow wave packet so that you know pretty precisely what the position is, then it turns out that the wave packet for wave numbers is very broad. And so you have no idea what the momentum is. And then conversely, if you convert it to a wave packet that has a very specific wave number, just one wavelength, like a laser beam has, a continuous wave laser beam with no packet, then you have no position for it. It's wherever the laser beam is, somewhere in that region. That was the point of this. So now the Heisenberg uncertainty principle, we're going to talk about that maybe after the first exam. So now I wanted to look at problems. So see, have either of you started on the homework? Okay, you did finish it?
Well, I did finish it, but then afterwards, I submitted it, but then I looked at the last problem, and I'm not sure I did the calculations right for the expectation values.
Okay, so let's look at that for the rest of our time to get some practice, and of course, make sure you know what you're doing as far as the calculations. So I hope you followed my recommendation and used a spreadsheet here for the second one. It makes life a lot quicker.
Yeah, I used your spreadsheet, but I also wrote it down so that way you had because I didn't know if you wanted a copy of that or not.
I actually, for something like this, I'd be happy with just you putting out a PDF of the spreadsheet and just giving me that. I can look at my numbers and look at your numbers and see if they're wrong, and I would trust that you didn't somehow randomly get the right numbers for wrong reasons. Okay, so look at the last one. Just starting at the top, we have this here, which is a Gaussian distribution. And so it says to plot the wave function. To a rough approximation, it looks like that, right? Should be symmetrical. And I didn't ask you if it's normalized, but let's start with that. Let's check to see if it's normalized. So not part of the homework. Is it normalized? What is the way to check to see if it's normalized?
Integrate it from negative infinity to infinity and see if that equals 1.
Perfect. And when you say it, you meant psi star psi. Yes. So let's do that. I, of course, don't have my integral table with me. Do you have it with you?
I actually don't.
Okay, that's okay. I'll just go to Moodle and get it from there. So we have the integral from minus infinity to infinity of alpha over pi to the, I'm going to put 2/4 power because I'm pedantic that way. It's alpha over pi to the 1/4 power squared. So 2/4, which we know is the square root. E to the minus alpha x squared, because e to the minus alpha x squared over 2 times e to the minus alpha x squared over 2 is e to the minus alpha x squared dx. So then we have to look at the integral table, which log in Sesame. Really? Sorry for that. How can it time out as soon as I click to submit my password? All right, so you guys have noted the Gaussian integrals right there, right?
Yes.
As of now, you have. Okay, so the Gaussian integrals, we have up here at the top some basic forms, and here is what we have, right? It's e to the minus alpha x squared dx, or a instead of alpha. So that's exactly what we have, except for the limit. It's going from 0 to infinity. So it's not perfect. How do we deal with that? This is where we use our basic understanding of integrals. If it's an even versus an odd integral, is this function even or odd?
Even.
Okay, it's even. And to make sure it's clear to both of you what makes it even, if I change from plus x to minus x, does the function change? If it doesn't change, it's an even function. If it changes from positive to negative, it's an odd function. If it does something else, it's neither. So this is an even function. And so for even functions, when you integrate the even function, you're going to have the same thing on both sides of 0. And so you just double it going from minus infinity to plus infinity. If it's an odd function, you would get 0 for your integral from minus infinity to plus infinity. You don't even have to do it. If it's an integral of an odd function over symmetric limits, it's going to be 0. So we just have to remember this for our first one. The integral from minus infinity to plus infinity of e to the minus ax squared is going to be 2 times 1/2, so get rid of the 2 and then 1/2, square root of pi over a, or alpha as our case may be. So this here is, and then our integral is and guess what that's equal to? Yay. That's equal to 1. Hopefully you recognize that was a pi and fat black. And those are alphas, the funny looking things. So yay, it's normalized. So now we can move on. If it wasn't normalized, of course, it should have had a constant like capital A out front, and you would find what capital A is. Calculate the expectation value for the particle's position. So expectation value is equal to, and what's the general formula? Perfect. That's the way that you should always put it in, because if the operator is not x, it might be affected by the function, such as the momentum operator. So I will this time be extremely pedantic. As well as very colorful. So here I put the different pieces in different colors. And now we can simplify. The x is not going to do anything on the function, right? It's just going to give us back x. So now I can freely rearrange to what you normally would have written out, putting the constant out front. We have the integral of x e to the minus alpha x squared dx. Who can give me the answer to that integral? You don't need to remember the table. You don't need to remember the table, because this is it an even or an odd function?
Oh, it's an odd function.
And so an odd function over symmetric limits is
0.
right. It's good to remember those things rather than knocking yourself out and getting annoyed.
So on the homework, can we just write that, or do we?
Once you get to here, you can say this is an odd function, so right. I mean that's solid calculus.
Yeah.
Okay, so the expectation value for x was 0. Hooray! We're all so happy. And then we have part C. calculate the standard deviation. What's the equation for standard deviation?
Square root of
the
x squared, x,
of the square.
yeah.
Yeah, that's okay.
Right. So we've got one of those terms already. Hey, I heard you guys saying the right things. I'm good. So now we just have to calculate the expectation value for x squared. So moving on. This is a really ugly color, I recognize. Now I'm going to ease up on being pedantic. I'm not going to write the exact same, well, hey, wait, I can do this. I can do copy and paste. And I'll be just as pedantic as before. Ah, crud. I wasn't this way until I became a teacher. After I became a teacher, I had to have things just right. Okay, so the only thing that has changed. Oh, come on. Didn't mean to change the color there, is that this is an x squared. And so that means it's going to be equal to, might as well do this again. Perfect. That's exactly where I wanted it, don't you know? Whoops. There we go. So now we have to look this up. Now this one is x squared e to the minus alpha x. Is that an even or an odd function?
Even.
Even. So that means we got to go back to the table. So look, there it is. Because it's even, we're just going to double it. And so instead of 1 over 4 alpha, it's going to be 1 over 2 alpha times square root of pi over alpha. So 1/2, or 1 over 2 alpha. I can remember that for 3 seconds. Well, that came out easy, didn't it? Now, how hard does life get? We can stay right here. What's the standard deviation?
Well, 1 over the square root of 2 alpha.
I had to put in the 0. Remember me being a pedant here. I couldn't leave it without. It's exactly what you said. I take it that's somebody outside your classroom.
Yeah.
Okay, so
When I-
go ahead.
When I did this yesterday, I found a different, like there was an integral for the x squared, but it was different. So my answer was like had a separate term when I did the standard deviation. So that's why I wasn't sure, because it didn't seem right, the answer I got. So that's why I was hesitant on
Mhm.
whether or not I actually did it right.
So, well, was your final answer the same? You say you got a different term, but-
First time, then I looked at a different integral table and it said that the integral was different. So then I did it the other way, and the other way was apparently wrong.
Speaking of wrong, at some point I moved my screen here, so my underline is no longer underlining what a, oh well. But this box used to be around that equation. Getting it back is never going to happen, so I'm not going to worry about it. Okay. Yeah, I guess we're 5 minutes early. I don't have anything else prepared. I was just wanting to look at problems for the end of the class period. Anything you guys want to talk about?
I guess, can we do another example of that, of the operator rules?
Sure. Problem is, how do I just coming up with an operator offhand is kind of difficult for me to just be random about it.
I mean, is there one that you use?
I'm sure there is, and I didn't bring my book with me. I remember I was planning on doing that. So yeah, can you find one real quick?
What chapter?
Chapter 1, section 5 to be specific. The questions tend to be at the ends of the sections. I think there's more at the end of the chapter, but well, here's one I can at least think up. Let's say the operator is equal to the integral of, so operator acting on f of x is equal to the integral of f of x dx. Let's just take that. Since we have derivatives, all of our operators are either going to be x times something or derivative or something like that. So let's just try this one. So if I'm going to test that, remember I have the two tests, one to test the distributive property. And so I would say is operator of on or acting on f of x plus g of x. So that would be our first test. You may or may not be quick enough to just say, I know the answer. If I do the left side, there I've done the substitution, right? But with integrals, you can always separate this into two separate integrals. And that's exactly what you would have. And so it passes that test. And then the second test is and so that's going to be and if A is a constant, that's true, right? You can move the constant in and out of the integral. And so this passes. Now that wasn't a very tricky one, but it was one. And of course, the key is just being able to check them and make sure. Why is that a key? Well, just because it's a rule. Our operators have to have that form. Okay, homework. If you have problems with the homework, well, Indy, you've done them all now and got the last one squared, or not Indy, Chris has. So Indy, obviously you can talk to Chris, but remember, don't copy his answers. If he explains them to you and you understand them, that's great. If you don't understand them, give me a call or send me an email, whatever, so I can explain further to make sure that you understand. The goal is clearly for you to get the homework and understand it and do it right, not for you to get frustrated and get a low grade on homework and say, if only.
Right. Yeah. Thank you.
All right.
So, one last question.
Yeah.
For homework, so on the homework, we had like three questions.
3 problems, yeah.
And so the first problem, obviously, there's an explanation that's needed.
Mm-hmm.
The second one, it's not really, as far as explanation goes, what would you want us to just explain what we're doing, or?
I would say just simple, and the statements I would say would actually be pretty much the same for both 2 and 3 because they're basically the same question. For applying a histogram or applying the function, obviously there's nothing to say. I plotted it, right? For the class averages, I'd say expectation value basically that's all you have. That's how you did the calculation. So I wrote down, this is how I did it. And then of course, you do it in the spreadsheet so you don't have to write down a whole bunch of times the same boring nonsense. And then for this one, the standard deviation, write it in words. Here I am already abbreviating. Standard deviation is square root, blah, blah, blah. So, having it spelled out so I know, yeah, he understands how the process was. It didn't just, I found an equation. Here you go.
Okay.
Right. So there's not going to be a lot of writing.